Okay, good afternoon everyone. First of all, let me introduce my colleagues. We've got Connor over on the right, we've got Joe in the middle, and myself, Sammy. As been said, we're from the University of Bath, and today we're going to speak to you all about physics, research, and STEM at university.
So as mentioned, we're physics students, and we're now in our final year, and as part of our final year, it's commonplace at university to sign off with a dissertation or a final year project. And the project we chose saw us come together as a team and with a university lecturer, and it's called Communicating Physics. Our lecturer is Dr. Peter Sloan, and he's a surface physicist, and the aim of this project is to inform and engage the public with some aspects of his research. It's often difficult to access university research and for members of the public to participate in, and that's why lecturers are keen to get involved with projects like this. So I guess why have we come to speak to you today? Well, previously our engagement activities have been targeting the upper ends of primary school and the lower ends of secondary school, as seen in the images where we took part in Bath Taps into Science, which is a science festival. Coming to speak to you today allows us to speak to an older audience who are further through their educational pathway.
So what are we going to talk about? Today, we're going to give you some sort of historical context and a bit of background into surface science. We're going to talk about a little bit of atomic manipulation and imaging and touch upon some cutting edge research that's going on currently. We're also going to talk about STEM and how that will be beneficial to you and our experiences at university. And also a bit about the futures that you can expect if you go and pursue a career in STEM.
Okay, so by now we should have a reasonable idea about scale in science, whether it's sort of cells in biology or whether it's molecules in chemistry. So we're now going to put our research into perspective.
So starting off at the observable universe, this is the largest thing known to man, and it's a spherical region of the universe comprising of all matter that can be observed at present day. There are at least 2 trillion galaxies contained within this observable universe.
Okay, so now we're going into the sort of scale of 10 to the 22 meters. This is the distance from Earth to the nearest galaxy, Andromeda. Now, put that in perspective, you could fit 10 Milky Way galaxies in that distance.
The Milky Way is our home, and it's a spiral galaxy, and it contains the solar system. It's got a diameter of approximately 100,000 light years and contains approximately 100 to 400 billion stars.
Now we're moving towards a magnitude of 10 to the 16 meters. This is about the distance of 1 light year, the distance light would travel during 1 year on Earth. You may also have heard of a parsec. This is approximately 3 times the distance of a light year.
Voyager was launched 40 years ago and became the first man-made object to exit our solar system and venture into interstellar space. Voyager has been travelling at 42,000 kilometres per hour for 40 years, and to put the speed of light into perspective, this could travel that distance in 1 day. There's some large stars called Cepheid variables. They're of the order of times 10 to the 13. And the largest star currently discovered is VY Canis Majoris. And this is Latin for big dog, and it's got a diameter of the distance between Neptune and the Sun.
Okay, so now we're moving on to a magnitude of times 10 to the 11 meters. Now you may have heard of 1 astronomical unit. This is the distance between the Sun and the Earth. As we've also spoken about light units for distance, this is about 8 light minutes long. And moving forward, we move on to about 10 to the 7.8 meters. Now this is about the size of Neptune, but furthermore, it's the size of it's the size of every map on the Minecraft game. It's quite impressive that humans have been able to create a game that size. So moving further down the scale, we go through planets to everyday objects, such as marathons, down to pyramids, down to the Eiffel Tower. and so on in.
Now we're arriving at sort of the average height of a human, which is about 1.5 metres. And as we get to smaller objects, go through like things like basketball, then small and even still to small animals like ants. And finally, as you approach the width of a human hair, which is about 1 millimetre, then humans can only see another order of magnitude smaller than that at times 10 to the minus 4.
Okay, so now we're moving towards times 10 to the minus 6.6. Now this is getting on to the sort of size that's a smaller size observable with an optical scientific instrument, such as a microscope. Now, anything smaller than this, the actual wavelength of the visible light spectrum itself is too large to interact with any of these objects. So we're now into the realms of computers actually analysing data and creating the images themselves.
And finally, at times 10 to the minus 10 metres, this is the size of an atom, the atomic scale. This is called an 1 angstrom, and this is where our research for our final year project, which is to do with surface science, this is the scale it takes place on. So that leads us nicely into surface science, and a brief introduction of surface science. What is it? It's basically the study of physical and chemical phenomenon that occur between two phases. Now, simply put, two phases and the interface between which are the boundary between two states of matter. So the boundary between solid gases, solid liquids, liquid gases, they're all surfaces where interactions can take place. A particularly famous example is catalyst interactions, where reactions take place on the surface of catalysts in order to help reactions go faster. So now we're just going to briefly introduce the science behind some of the tools used within surface physics and chemistry. On the top left image you have a diagram of the piezoelectric effect. The top right image is of quantum tunneling, and the bottom image is of wave-particle duality. And hopefully in the next couple of minutes we're just going to describe each of these phenomena and explain how they all contribute to imaging and manipulating atoms using the scanning tunneling microscope. So, we've discussed three phenomena that are used within the STM. So now, how are they used to image and manipulate atoms? Well, on the diagram on the board, we've got the setup illustrating a scanning tunneling microscope. We can see that the STM has a tip of a single atom, and when this is brought very close to the surface of our sample, which is called a substrate, and this distance is within nanometers, so 1/1,000,000 of a millimeter on your rulers. A potential difference is applied across our substrate and the tip, and this causes electrons to tunnel from our tip into the sample. Because this gap is small enough, they're able to tunnel across and cause a flow of electrons which produces a current, and this is called a tunneling current. This tunneling current is proportional to the size of the gap. Therefore, if we know the current, we can calculate the size of the gap. So when imaging the substrate, the STM is set to maintain a constant tunneling current as the tip uniformly scans the surface. This means if the surface goes up, the tip has to go up in order to maintain the same gap, which will maintain the tunneling current. So if the tip is following the contours of the surface, we can run this data through computer software and visualize it on screens, as seen on the next slide. here's a couple of images taken by an STM to give you an example of the detail that can be achieved. The top left-hand image is of a uniform surface, and each of the yellow peaks is an individual atom. The top right-hand image, in green, is a copper surface, and to the eye, this will have been as smooth as you can possibly achieve by filing it down and polishing it with ethanol. But as we can see in our image, there's in fact a fault on the surface. To give you an idea of how big that image is on the surface of the sample, each side of that square is 500 nanometers in length. And in order to take an image like that, the tip of the STM will have been 40 nanometers from the surface.
Okay, so now we move on to a further major use of the STM. Its ability to actually manipulate the very atoms that it can see. It does so through using three main techniques. First one being tip crash, the second one being vertical manipulation, and the third one being lateral manipulation. So we're going to start off with tip crash. This is commonly used before manipulation is started. On the outset, it may seem very destructive, creating craters on the substrate surface under investigation. However, tip crashing has many intuitive uses. It's used in the tip apex construction, as seen in the left diagram. The tip needs to be one atom thick, and knowing its chemical makeup of the apex is crucial for the STM to manipulate efficiently. When the tip is collided with the substrate, some of the substrate is actually found to coat the tip of the probe. By doing this, the apex will then have a known chemical identity and a one atom tip. So in this top right image, in A, the actual tip itself had a different chemical composition to the substrate, which is why the image is appearing blurred. However, in B, the tip has the same chemical composition as the substrate, and so the atoms are actually, that you're wanting to look at, are protruding off the surface and are easy to see. In this bottom diagram, at the top of this, you can see the crater where the probe has entered, and underneath, lots of silver dots, which are actually individual silver atoms thrown out from the crater. Now, these silver atoms can actually be manipulated, as we'll see slightly later on, and can be manipulated into objects and lines and even machines. Okay, so moving on to vertical manipulation. This form of manipulation involves the transfer of atoms and molecules between the tip of the probe and the surface material. When an electric field is applied over the surface of the material, the atom will jump from the surface to the tip apex. The STM can then move vertically and laterally until we get the atom to its desired location, whereby this process can actually be reversed and the atom can be dropped to its desired location on the substrate surface. Finally, we're going to look at lateral manipulation. Now, this is used to relocate atoms across the surface of materials using forces. When the probe is brought close to an atom of a certain element, a chemical bond is formed. This is stronger than the interatomic bonding of the atom and the flat substrate that it sits on, and so the atom can be displaced. If the probe is pushed towards the atom, the atom will be pushed along the surface. Doing this in reverse will actually pull the atom. The probe-atom relationship is then destroyed when the bias across the surface is removed. So finally, we move on to a combination of the manipulations. So as we can see from the diagrams, you start off with a molecule called sexyphenyl, and basically the tip crash is used to create trenches and silver atoms, and the manipulations used to move the silver atoms as barriers along the edge of the trench. The lateral manipulation is then used to pull the sexyphenyl along to about halfway down the track, whereby the probe is increased in height. Therefore, the interatomic attraction disappears, and there's a small probability that the sexyphenyl molecule will actually combine with the silver atom. Now, through doing this, scientists know that the sexyphenyl can actually crawl across the surface of the molecule when there are no forces involved, by alternating the direction of every second benzene molecule in its structure. So it's known as a quantum caterpillar effect.
Now, these techniques are clearly interesting and, pretty in-depth and high level. But how actually are they going to be used? Well, in drug delivery. For example, the STM tip can be coated in a new type of drug that that can't be absorbed readily easily by humans, and it can be placed into a molecule of different structure that can be absorbed by humans, and therefore we can easily take a molecule of the drug. Also, nanotechnology, electronic efficiency, solar panels, that kind of thing, and in particular, nanodots. Nanodots are very easily created by STMs, and they're a small part of component that can be used in quantum computers. Normal computing uses a binary one-on, one-off sort of basis, whereas quantum computers can access almost an infinite level of energy levels that the nanodots can provide. And finally, the STM can be used to break down environmental pollutants. The STM has already been used to cut benzene molecules apart, and benzene molecules are one of the key components of PCBs, which is a very harmful chemical in the environment. If the STM can be applied to these chemicals in our environment and cut them apart, this can be very useful for the future of our planet. Touching more on the nanoelectronics, something that's actually happening today, or in the present time, is a chlorophyll molecule that's being injected with electrons by the STM. Now, these injecting electrons change the orientation of the chlorophyll molecule, as you can see in this image up here. But what's really interesting is that when the chlorophyll molecule changes orientation, it has different resistances or can lead to bigger or lower currents. As you can see in the bottom right-hand corner, it looks like an on-off current, which is exactly what you would expect from a 4-step switch. But this 4-step switch is on a nanoscale, as opposed to millimeters, as is currently being used.
So you want to hear a bit about myself? Well, at school, in my final year, I went to school in Scotland and I studied physics, maths and chemistry. From there, I refined and went into mathematics and physics at Bath University. From there, I was lucky in that I got a placement with a brokerage firm in London. That brokerage firm quite liked me and told me that I had a place there upon graduation. So basically, I'm going to skip the grad role there because they thought I was all right. And I'm basically going straight onto the desk, working 6 in the morning until 9 at night, which sounds great. My 5-year plan for the future is basically I want to work abroad. I want to work on Wall Street in New York. I want to work in Singapore, Tokyo, and potentially Sydney as well. With that, I also potentially want to change desk just to get an experience of all the other products that I could possibly grow.
Similar to Sammy, at school when I was studying my A-levels, I was studying STEM subjects, chemistry, biology, physics and maths. These went well and managed to get into Bath University to study physics. I decided to pick physics because it was the one I was best at in school and most enjoyed. I realised as soon as I got onto the physics course in my first year that I didn't want to do anything to do with research or science research as a career path. So I used my summers to get internships at places like Shannon Rail, which is a construction company on railways, and the Murphy Group, famous for their green vans. And we were I was in the tendering office working on a project in Hinckley, which linked very nicely with my physics because it was about the construction of a new nuclear power facility. Gone back to university throughout semester, and now in my final year I applied to different grad schemes within construction and engineering sectors, and I've been offered roles within construction management and project management with Lang O'Rourke, Murphy's and Carillion. Hopefully I'll make a good decision which company to go to and progress over the coming 5 years out of their graduate scheme and onto their big jobs, with the ultimate aim of becoming a senior project manager or even more higher up the level within the companies to board members. And there's also scope for these big companies to work abroad with countries such as Australia, Singapore, Hong Kong, Canada, jobs going on there and around the globe.
Similar to these two, at school I did maths, further maths, physics and French. I came to Bath, started doing the physics course. I've been really enjoying it, but what I realised while I was doing it is I just don't want to be stuck behind a desk. Right? Luckily, I'm able to do teaching opportunities like this, for example, and I realised that I really enjoyed it. So, going forward, what I'd really like to do is do a really high-powered teaching course, which the links in my university will provide for me. And at the moment, the government are giving big bursaries to STEM teachers, which again is another incentive to go into STEM. Going forward from that, what I'd really like to do, like these two, is travel. But in my way, I'd probably be going around teaching English to people in like Vietnam, in Africa, maybe in Asia as well, in China and Japan. And then hopefully, what I'd like to do is explore my options. Maybe become a head teacher somewhere, or if I want to move into this private sector where there's a bit more money, that's what I desire.
Finally, I'd just like to take this opportunity to thank you all for listening to us today. We hope we've sparked interest in furthering your STEM careers and maybe looking at STEM at university. We also hope you found interesting and insight into the Bath research and surface science. Could you please take 5 minutes just to fill out your evaluation forms that were given to you on the way in? And if you've got any questions, we welcome them. Thank you very much for taking part in our 5-year project.